Hey there, my name is John Pacific. I'm a cryptography engineer at NewCipher. I'm going to be showing off Sputnik, which is our ETH Berlin hackathon winning project. Sputnik is an assembly language and interpreter for fully homomorphic encryption. We use this to execute the first ever fully homomorphic smart contract to win the hackathon. Before we continue any further, I'm going to say that this is a proof of concept and that you should not use it in production yet. You can view this code at github.com/newcipher/Sputnik if you ever feel like playing with it yourself. Okay, so let's just jump right into the demo. First, I'm going to be importing some libraries we need to actually execute this demo. And here I'm going to be going through this line by line. So Sputnik Parser is what is used to parse the Sputnik smart contract I have defined here. And essentially it pulls out some symbols and things like that so we can actually execute it and interpret it. The Sputnik program, what we call get program, which I call proggy, that is essentially what holds the state, such as like an execution pointer, which line of code we're executing, and like just various things about like what variables are in the contract and everything. This here is the Sputnik Engine. So this just simply executes the code and tells us which things we're executing. Here I'm reading a Viper smart contract, hash header, written by Michael Igorov, our CTO. And it simply just you can add hashes to it and read hashes from it on the blockchain. I'm reading the contract code here, and then I'm deploying it to a test blockchain I have up using geth-dev here. So as you can see here, it has now been posted to the blockchain. So continuing on, this is using NumPy. We use it for random number generation because it's pretty simple. It's what makes it really convenient to do certain math with, specifically for like different types of random numbers that we need to generate. It's insecure because it's not technically cryptographically safe, which is fine because we're just doing this as a demo and you shouldn't be doing this in production. But yeah, we use this for mostly a lot for lattice-based schemes, which NewFHE is what we use, actually uses that. So next we're actually setting up NewFHE. You can see NewFHE on our GitHub. That's github.com/newscipher/nufhe if you want to see that library. So we're simply getting two outputs here, a secret key and a bootstrap key by calling make key pair. So what this exactly means is our secret key is actually what we use to encrypt data. All right. So currently NewFHE only does things in symmetric encryption. You have to know the key to encrypt and decrypt. You have to know the secret key to encrypt and decrypt. The bootstrap key specifically is used for actually doing computations on the encrypted data. This is how fully homomorphic encryption works. Any party with this bootstrap key can perform the computations on your encrypted data. So this is technically a public value and you can hand it out, though you should also still be careful about who you give that out to only let them do computations if they should have access. The size that we're setting here is what we would pass around to other NewFHE calls. Essentially, we're just setting the size of the ciphertext state. In this case, we set it to 32 bits. Notice that it's bits, not bytes. So in this case, we're creating a ciphertext that we can use 32 bits of. Because FHE is currently rather experimental and in a research state, the ciphertexts are quite large. So you can imagine about 2 kilobytes per bit. So we can continue on with that said. Things are going to take a little bit longer to execute than they would normally for anyone else with a decent graphics card because I'm running on an old MacBook and also recording the screen at the same time. So next, we're setting up our plain text and pad, and then we're going to encrypt it. So right here, what I've created is a NumPy array of bits. And we're using false and true because it's relatively simple to just say 0, 1 there. But it just makes a lot of sense doing this. So I've made a pretty obvious pattern here. As you can see, false, true, false, true. And so you should be able to recognize the plain text rather easily. The pad here is randomly generated. So we're setting up the same thing as this, as a NumPy array in the 32 bits. So we're just creating an array of 32 bits with random data filled in it. And then here, we're calling newFHE to encrypt our data. So in this case, enc plain is the encrypted version of plain. So we use the secret key, we pass in the plain, and we pass in our Sputnik engine here. And we also do the same thing for the pad here. So once this is completed here, enc plain and enc pad will be encrypted. And I can show this by doing A. And you can see that this is essentially the encrypted version of the array here. And we get two forms of this. So we get two values in, just like this. These are all of our encrypted values inside of this array. So we went from this to this. This is just simply encrypted. This is how learning with errors works, and how our fully homomorphic encryption newFHE works. So you can take a look at these two commands again. We just call newFHE.encrypt. Next, we're actually going to execute the homomorphic contract. We're going to get two outputs on this. We're going to get a contract state out and a Merkle tree. I'll go into detail on what the Merkle tree is for later. But simply, we're calling the engine and telling it to execute this program. So what we're doing is we're passing in our plain text and our pad and our test key, which is the bootstrap key, which I explained above earlier. So for our plain text, we pass in our encrypted plain text, and for our pad, we pass in the encrypted pad. Let me pull up the contract code for you. So as you can see here, we're performing a one-time pad homomorphically. What exec does here is it simply declares the entrance to the program, and we're setting up two variables to begin execution with. So in this case, in the case of Sputnik, you have to pass in these two variables to actually execute the code. You can't not pass them in. Very similar to just how you execute smart contracts on the regular Ethereum blockchain, you actually need to pass in some variables to actually begin code flow. With the key opcode, we declare the variable for the bootstrapping key. And then for size, we declare the size of the ciphertext as in 32 bits again. And here, since a one-time pad is very simple, we just XOR our plain text with the pad of the same size that should be completely random and never repeated. We simply XOR the plain text with the pad. Every time you call a logic gate in Sputnik, you're going to change the state. So whenever this is what the result of this XOR is, sets the state. And then when you call exit, it returns the state. So I can show you here. After this contract is done executing and you call exit, you're going to return contract state out, as well as that Merkle tree, which essentially just has hashes of the computations. So let's go ahead and execute this program now. It is going to take some time because my graphics card is not great on this machine. All right. So now we have our output done, and this is an encrypted output. So contract state out is still encrypted. What you've actually done is essentially the encrypted version of plain XOR pad. So I'm creating a reference in the plain text. I'm going to just go ahead and perform this one-time pad on the plain text here, just to prove that it is the exact same operation. So as you can see here, I set reference to be the XOR of plain and pad, which is exactly what we did here. We simply XORed plain and pad here. The only difference is that in the Sputnik contract, this XOR happened on encrypted data. So at no time was the computing party aware of what the plain text or the pad was. All they saw was encrypted data, and they performed a logical gate on it. So here, dec FHE ref is what I'm calling on the contract state out. So if we recall, contract state out is encrypted. It is the encrypted version of this one-time pad performed here. to actually compare this to the reference, I'll need to decrypt it first. So I call newfhe.decrypt, and I pass in our secret key to decrypt it, and the variable that we're decrypting. So I'm decrypting the state, and I get decfheref. So now I can actually compare the two. And as you can see here, the output is all true. So the output of this operation is the exact same as if it was done in plain text. So that is what fully homomorphic encryption is. It allows us to perform computations such as logical gates, such as XOR, AND, NOT, etc., on encrypted data. This is very, very powerful, and we believe it to be the next generation of privacy computing. So continuing on, we're going to commit the root to the blockchain and print it. Now I'm going to go into in depth and explain what this is, because this is sort of a little hacky workaround, since there's actually a fundamental problem, if you know anything about fully homomorphic encryption, is that anybody can actually perform any computation. So there's nothing that prevents the computing party from doing the XOR that you want them to. They could actually do a whole bunch of different operations on it and then pass you that output. This is an open problem with regards to smart contracts. The way I've gotten around this in a hacky way is sort of allowing us to do verifiable computations so that we can upload the Merkle root of all these computations and then check the hashes of each output to verify that the computation was done correctly and that everyone else can come to a consensus. The way you might use this is with a TrueBit style of consensus mechanism. So let's go into the smart contract here. This is the smart contract that Michael Ugrov wrote. Essentially, it just allows you to add hashes to an array and read those hashes. That's all it is. It's a very simple and just quick, hacky contract for what we wanted to accomplish. So that's all I'm doing here, is on this Merkle tree that I get out, if you recall, I get a Merkle tree here as an output of my program. I call get Merkle root, and I push this Merkle root up to the chain. Now, let's go back to our Sputnik smart contract. After every single XOR, after every single logic gate that you call in Sputnik, you're going to be setting the state. And you're also going to be adding leaves to a Merkle tree. So in this case, the output of the XOR gets added to the Merkle tree, but also the hashes of the ciphertext as well. So we get a hash of the encrypted plaintext and a hash of the encrypted pad, and that gets added to the chain to the Merkle tree as well. So at this point, once this line is completed, we actually have 3 leaves. We have, this is our 0th leaf, our 1st leaf, and our 2nd leaf. Okay? So what we're essentially doing is adding this as a leaf, this as a leaf, and then the entire computation here as a leaf. This allows us to verify that some computations are done correctly. And you can see here that I can verify that logic computation was done by checking the blockchain. The way this works is I simply call the contract and I just read which index I want to read from the smart contract. So this is just the output. This is what this is here. Okay? So with the Merkle tree, we can actually generate proofs. So for example, if I wanted to get the proof of the XOR, I can do that. You can see this here. And so with that proof, we're actually able to pass in this root here, the Merkle root, and the target hash of the ciphertext to validate that the computation was done correctly. So this is actually very powerful for us in that we can somewhat come to a consensus using something like TrueBit style consensus or something to agree that a computation was done correctly. Obviously, this is not ideal, and the preferred way would be to do a zero-knowledge proof on the computation itself. So for example, going back to our contract, it would be great if we could do a zero-knowledge proof to prove that an XOR was actually computed, and not just any arbitrary computation. So this is Sputnik, essentially. And we think it is just a great proof of concept to show how a fully homomorphic encryption can be used to show the future of smart contracts and fully homomorphic computing. So we're very excited at NuCypher to begin our research on this and make it much more practical. So again, you can see this if you go to NuCypher, github.com/NuCypher/Sputnik. Yeah, so thanks for watching, guys.